Good afternoon. Thanks for having us here. I'm going to speak for a few minutes, and then Rob is going to do the real talking. He was introduced as head of the math department. Rob is a little bit more than that. He's head of the math department. He's acting head of the science department. He also has an MFA in poetry, has taught poetry. He hosts a poetry website called Sixth Finch, just the kind of teacher that we need in all our schools. I'm going to take a few minutes to provide some context for Rob's presentation, because the beauty of it, the power of it, I think, is that the approach happens, needs to happen in every classroom, at every grade level, in every course. Initiatives that stick, change that sticks, needs to come from an organizational mindset, and I think schools need to be a lot better at developing an organizational mindset. As Phil indicated, I think the last 2 days have been about much more than about math education. I think we're talking about where education needs to go. Rob's going to mention our work with coding at Beaver, and our coding initiative, which has kids learning to write code eventually within all their courses, is no standalone initiative. It's meant to have an impact on every kid, and our organizational mindset is that if something's important, every student needs to experience it. And we don't have time actually to be thinking about where education is headed. We've got to figure out where it needs to be right now, and that's a big piece of our educational mindset. In Rob's examples, he'll be talking about math instruction in at least three critical areas of emphasis for education. One, we really need to commit to dramatically expanding the very nature of what's possible for kids in what we now call school. There was an analogy yesterday, you know, if you have a dirty house, you kind of work on one corner and you know, nudge away at it. I think we're beyond that. My analogy is if you got a house that's full of fleas, what do? Yeah, bomb it. And I think that's really more where we are. We need to commit to teaching students the new basics, creative problem solving, collaboration, hugely important, visual communication, presentation skills, technological and media literacy, empathy, iteration, also hugely important. You can add your own, or as I call them the new basics, as Joe Bowler said yesterday, these are the Fortune 500 skills. And if we don't teach these skills, we're really undereducating our kids, and we probably need to find out how to assess them, I think. And we need to commit to hiring, developing, and retaining teachers who are genuinely excited about what the future holds for our kids, even if they don't know what it is, and teachers who are both and thinkers, who aren't afraid to be beginners. One of the great things about technology is that used correctly, it puts kids in a position where they're content creators, not just content consumers, in all their disciplines and projects. And as content creators, they'll be doing work that counts, that really matters to them. Plowing through problems 1 through 30 even doesn't count. It doesn't matter to kids. It never has mattered to kids. I remember doing that. Rob's going to be talking about what he calls real, not realistic work, real work for kids to do, not just realistic work, work that sticks, again, actually work that actually matters to them. One way to see if a teacher is really engaging with and connecting with kids, you go into a classroom and ask the kids 2 questions. What are you doing, and why are you doing it? It's a great evaluation tool. What are you doing and why are you doing it? This isn't just about math. I mean, not just kids in other disciplines ask, why are we doing this? I used to be an English teacher, you know, so Mr. Hutton, you know, if Emily Dickinson thinks life is cruel and arbitrary, why the hell doesn't you just say that? And why do we have all these riddles? You know, and you had that's a good question. You got to have an answer for that. So what are you doing? Why are you doing it? So this one I can't emphasize enough. We need to put to rest the ridiculous notion that in school the goal is to get it right the first time. In real work, if you get it right the first time, you didn't get it right even in math. We have this program that we do called NewView. It's over in Cambridge, long story. The kids spend a whole term over there. And prototyping is a huge part of that program. And last year we had a kid coming back, and he was talking about one of the projects that he did. And he was really excited. And he said, you know, my team had the record for the most prototypes ever at Newview. We had 17 prototypes. That's a mindset kids have to have. He didn't say, Jesus, it took us 17 times before we got it right. He was excited that they did that many prototypes and stuck with it. And it's important for teachers to iterate, to model. One of our mantras, borrowed from Dan Pink, for kids and for teachers, especially for teachers, is make excellent mistakes. If you tell kids iteration is great and assess them with questions that have right and wrong answers, you're telling them to get it right the first time. And along the way, we might even put the rest, the idea that all learning has to be linear. So now Rob's going to provide 2 examples of how this all plays out in our math classrooms. And yes, math and coding is a piece of this. Rob? Thanks. Where do you want me to
All right, so the first example we're going to take a quick look at is an algebra example. Students building catapults out of, well, you'll see, clothespins and popsicle sticks and rubber bands and a bunch of strange little products. The idea here is that at a lot of schools you see kids learn the basics out of a textbook, out of lectures, and then eventually, maybe if they're lucky, they get a chance to apply those content skills to some sort of creative project. We just do that process backwards, start with the thing that the kids are going to be engaged by, the thing that they want to do anyway, and just embed those content skills into those activities that are engaging. So jump right in, and our kids are learning about quadratic functions, parabolas, in the context of something that they enjoy. So we're not giving something up. We're just teaching the same content in an engaging way. This began as a fairly structured teacher-designed project where the goal was to hit a target. And over the past few years, it's evolved into something that's much more student-designed. The kids on their own decide what the goals are. They define the goals. So some years kids might say, we want a catapult that shoots the furthest. We want one that is the most cost-effective because they've got to buy their supplies. We want one that is aesthetically pleasing. They're coming up with much more sophisticated goals for the project. Students are also deciding what sort of technologies they want to use as they're doing this work. Instead of having a teacher tell them, here's an Excel spreadsheet, you need to use this, and here's how you need to use it, and here's a model of how to use it, we let them loose and give them access to a range of different technologies. Some students will choose to use a spreadsheet. Other students will, on the fly, decide that they should film the catapult shooting M&Ms down the hallway and collect data through their phones. Letting kids make those decisions and like Peter was saying, make some excellent mistakes, generates much more sophisticated learning. This project used to also be a one-shot deal, no pun intended there, that they would fire the M&M, you either hit the target or you don't. We've got much more iteration in the process, so kids are working in teams, coming up with an initial design, and then looking during a testing phase at what works and what doesn't, and a lot of cross-pollination going on. Peter mentioned the coding initiative. We've got kids in all of our classes, 6 through 12, with opportunities to write code, but it's being done in a very organic way. So during this project, if kids realize that it would be nice to have a simulation, a virtual prototype, then we help them, we support them in building that. We're not forcing it, we're not telling them that they have to build it a certain way, we're just giving them support when they want to use that sort of technology. And about assessment, which has been a topic that keeps coming up. The assessment in this project is happening constantly. It is a constant feedback loop. Teachers are walking around the room, providing support, asking thought-provoking questions, and assessing every single step of the process, not just the end result. Some other examples so that you can see the range of messy glue gun devices. And then I'll jump into another project we've got. Back when we used to offer AP courses, and I'm very happy that those days are over at Beaver, it was a little frustrating to me teaching AP Calc that I didn't feel like I could justify taking time out of that structured curriculum to do a project where students were designing roller coasters. We got rid of AP, we had a lot more freedom, still could do work that was just as rigorous, even more rigorous, more sophisticated, and have room for more project-based work like this. So instead of just using the sort of textbook methods to present ideas of velocity and acceleration, again, throw students right into a real project, ask them to design a roller coaster for a theme park, leave it fairly open-ended so that students on their own can decide what factors they think are important. And on their own, my students determine that things like safety, things like marketability, excitement, trying to quantify excitement. That's a good task for a calculus class. So they come up with those sorts of questions, not just the answers. They're the ones coming up with a lot of these questions. Again, the project has evolved so that there's a lot of iteration. Early on, groups tended to jump to Excel or some sort of spreadsheet, write functions to represent the height of the roller coaster, calculate velocities, accelerations, etc. That wasn't a bad project. When students started asking me if they could create simulations, it turned into a much better project. So I've got students in the room who've got some experience with things like 3ds Max, SolidWorks. If they ask me, can I make a model of our roller coaster, the answer is yes. If students say, can I write some code to create a simulation of our design, the answer is yes. Again, students have a lot of control over those decisions, and our students are choosing to do very sophisticated work. Let's see, I'll give you a quick glimpse of tying these two presentations together that you will see a turtle there. So for a student who had absolutely no coding experience, but who was motivated to create a virtual model of their group's design, I pointed her towards this language, which is now called pencil code, which is a variation off of Logo, and she was able to jump right in and create a fairly sophisticated model with a little bit of support. I wanted to talk in general about both of these projects and some of the big themes that come up here. I want to emphasize that we're not cutting content. We're not a school that's saying, what can we give up in order to make room for this kind of education? Our kids have all the same content skills that students at other schools have, and more. This year in my calculus class, I got through the end of September and looked at the content we had covered through this type of education and realized that we were basically halfway through October compared to what I had done the previous year. So I will argue that this approach is much more efficient. I hope there are enough math teachers in the room that this resonates, that in the traditional model, you teach in a traditional way, the kids are not particularly engaged, and you find teachers having to reteach the material because kids didn't absorb all of it. And we shouldn't be surprised because it wasn't very engaging, so we shouldn't be shocked that they didn't absorb it the first time. If we can engage them from the beginning, then you're cutting out all of that review time, and that review time turns into time where you're covering new content, and you're digging deeper, and you're asking more complicated questions. And we've found that that's exactly what plays out. Our kids do fine on the standardized tests, but they also have great collaborative skills. They can think outside the box. They're resilient. They're not afraid to make mistakes. So we're doing that both-and approach, and it's working. I think that's probably a good place to stop. I'm hoping that we'll have some good challenging questions from the crowd that both Peter and I can try to answer.